Hi, hope you all are okay. And it has been a long time that we have not met, and I think you all are studying well. Mm. So, in our last classes, we have discussed Coulomb's law and application of Gauss's theorem, and have done various problems. Uh, uh, so, this time we are I am planning to teach dielectric properties of matter. So let's start. So I don't know how much will I able to uh, teach you by this video, but I will try my best. So before going to the main topic, we need to know some basics of uh, dipole dipole moment and its applications. Okay, then we will go on to the dielectric of the matter. So, if you see a charge distribution from a far away, you will treat the charge distribution as a point charge, and if you zoom in the charge distribution, you can see various type of distribution, like you can see dipole, quadrupole, octapole. So gradually you will know how this type of distribution looks like. So if we treat a potential uh, in such a way that we will see different charge distribution in the expression. So let us write the potential in this form. You know the form already, we have discussed in our class. So if I expand this curly r in this way, you can see here. And if I consider that this epsilon is very small, why this is small, you can understand by the expression of epsilon. Okay, what is epsilon? That r dash by r and multiply by this factor. Hmm. So uh, if you already I have talked about that I am dealing the problem from the from very far away, right? So obviously this r is should be very much larger than this r dash, right? So naturally this epsilon will be very small, so we can draw a approximation about this epsilon. So we will expand this one by infinite series. Already you have done this type of expansion in your plus 2 level. You can remember this 1 plus x to the power n equals to this. So if we expand this Carlier, I mean 1 by Carlier precisely in this way, so then if we, you can see, replace again epsilon by the real term what we have considered as epsilon, then we will get this expression. You can do it at your home, or you can see any standard book, you will find these expressions. And finally we will get this type of expression. And we can express these expressions in a general way. So perhaps you have not learned this legendary polynomial. So I think third semester you will learn these things. So for the time being, just you just consider uh, or assume that these are like the legendary polynomials are like this, that p0 x equals to 1, p1 x equals to x. So if you replace x by cos theta, then you can find these expressions. Please do it carefully or notice it very carefully. So you can find the same thing here. Analogous to these polynomials here. You can find the terms here. I can write this 1 by Carlier in this form. Uh, so finally we will get VR, potential, as this type of expression. We are calling this 1 by r expression as monopole, and 1 by r square as dipole, like this 1 by r cube is quadrupole, and 1 by r to the power 3 as octapole. Uh, mm, Later we will do more simplification for dipole. Uh, now we will see what type of distribution for monopole, dipole, and quadrupole. So you can see here that obviously monopole is should be consist of one charge particle. That is here, as you can see. For monopole it is varies, potential varies as 1 by r. For quadrupole, you can see the charge distribution, it is 1 by r cube, and dipole it is 1 by r square. Octapole obviously v varies as 1 by r to the power 4. These are the actually charge distribution. Now, if we treat the dipole, as a simple electric dipole directly, that by direct calculation, if we want to find out the potential of a electric dipole by direct calculation, then we can do it in a simple way. You can see here from the picture it is clear that I am considering plus q and minus q and separated by d, and it is treated as a dipole. And if I want to calculate potential here, then obviously if you apply the simple formula, you can find this expression 1 by 4 pi epsilon 0 q by r plus. The r plus, Carlier plus is a distance from plus q to the point where I am going to find potential. And similarly for minus q. And if I simplify this Carly R plus minus, simply if you can see that it's simple, that already you have done this type of expansion in the vector analysis, right? So if theta is the angle between this d by 2 and r. So easily you can find this curly r's. So this is a simplification. And if I assume that this d by r, that means r is very greater than d, then I can neglect this d square by 4r square. Hmm? Uh, this is simplified by this expression, and again I will apply the binomial expansion. I mean, not yeah, it is like binomial expansion. So I will get this one, and if I try to find 1 by r plus minus 1 by r minus, I will get d by r square cos theta, and finally I will get potential as this term qd cos theta by r square factored by 1 by 4 pi epsilon 0. Now I will try to draw a comparison of this potential by direct method, and also uh, what we have got by multiple expansion, right? Then we'll understand that both the term are actually same term. Okay, let's see. So this left-handed portion is from the direct calculation, and this right-handed portion from multiple expansion. So let's first treat this left-handed side. Okay, so here you know that the dipole moment, magnitude of dipole moment is qd, right? You know, all of you know, I think, charge and distance, I mean separation distance. And if I perform p dot r unit vector, that is that direction, in a unit vector of the direction where I am going to calculate potential, and I will find this one. If you look at the picture, the thing will be very much clear to you. Mm, so if I treat p as a vector, so direction will be minus q to plus q, right? You know that the direction of a dipole moment is always goes from my minus charge to plus charge. Then I will get potential as this like expression. And for the multiple expansion, if I try to simplify it, you will so r dash cos theta dash will be written, can be written as r dash unit vector dot r unit vector. If you look at the figure what I have drawn previously, you can find the thing actually. And also you know that dipole moment is simply the distance, and I mean from the source of the source coordinate, I mean source coordinate into charge density. Charge density, that is it is actually the total charge, you know, rho r dash dv dash. Hmm? So elementary charge actually, doing integration, and I will get the total dipole moment, right? So if I replace all those things here, so I will finally get the same expression what I got from the direct method. So simply we can say that the both the dipole I mean potential from the dipole moment is same. Now we are going to find out electric field. So from the expression it is clear that uh, the we have treated the dipole moment and potential in the spherical polar coordinate, right? So simply if we want to calculate the electric field, we have to apply I mean we have to do all the calculation in the spherical polar coordinate too. Hmm? And so for the simplification, we have considered this dipole moment in the direction of z for the simplification, and finally we will get a expression such that the expression will I mean, signify a dipole moment in any direction. Okay, so for the time being we are considering in the z direction. Now if you see, so this potential is simply we have written p cos theta by 4 pi epsilon r square. So I will find out the radial component of electric field. So it is very simple. If you if you see that what is the expressions in of expression of gradient in spherical polar coordinate, so you will find that it is radial component is actually the partial derivative with the r, and for theta component is 1 by r, del by del theta, right? So as usual for phi it is like this. So we will find potential, sorry, electric field components. So we have got these expressions, and if we represent in a vector form, we will find this expression, right? Now we will try to uh, find that expression with the only vector form, not any theta like this form. I mean, cos theta sin theta. There will be no cos theta sin theta. Only we will find the expression as a dot product. So simply, already I have told that um, P is aligned to the z-axis, right? So, so uh, surely P has R component and theta component. So it is like this. Please think about this components, especially for P theta. Hmm. Why it is minus, you will understand if you look at the figure. You can understand this thing. Now if I modify the equation for electric field like this, then you will find these expressions. So this is the expression. So in exam you may be asked with this expression. You can find in this way, or there is also another way. Please look at other standard books. You will find this type of expressions. Hmm. So now we will find force and torque on dipole. So there is a two condition, when the electric field is uniform, another is when the electric field is non-uniform. So first we will find an uniform electric field. So simply, since the electric field is uniform, so simply we can say the force are actually QV and minus QV. You can, it is very clear from the figure. Hmm. So naturally, torque will be like this, you know, hmm, R plus and uh, R plus cross plus and R minus cross F minus. If I replace R plus by D by 2, you know it is D by 2 with respect to origin. And if I replace forces, I will find this expression P cross E, or you can say P is sine theta, right? Now we will treat the thing in uniform field. So first we will find out the force. So since it is non-uniform, so you know there will be a difference in two forces actually. Hmm. You can see here that obviously uh, So this is like that uh, again q u e plus and minus q e minus, and we can find q into delta e. Now for delta e, already I think I have done this type of thing in class. If you remember, we have expressed uh, delta potential or dv in a grad form, right? Or you have done in your vector analysis class. So you can find delta E equals to like this, delta Ex dot D. Since D is infinitesimal length, I have not written it as delta D. If you remember, then dv equals to grad v dot dr. Mm, you have already done this type of expression. If you I mean break the thing, you will find actually dr. Hmm. So it is it can be written, it can be rearranged in this way because it's dot product. And so applying associative property, we can write this thing. And finally we got force as P dot grad E. Now about the torque. So at the center, first of all, what will happen at the center? Uh, a dipole is infinitesimal length. Already I have talked that dipole is very tiny. So at the center, torque will be same. I mean, what we have calculated in the previous section for the uniform field. Now, if we want to calculate the torque at other points, okay. I mean, if I think that this is non-uniform electric field, if I want to find, I mean, torque at other points, then since there is a net force, net force. Already we have calculated the force. There will be a net force due to this non-uniform electric field. So there will be extra term, and that is R cross F. So finally, at other point, torque will be P cross E plus R cross F. Okay. Now we will find the energy of a dipole moment. Hmm. So in this figure we can see uh, uh, so what will be work done in is the actually equivalent to the energy, you know it. Okay. Hmm. So if I find the work done, then I can say that this is actually energy. So here if electric field aligned to the y-axis, you know that the dipole will tend to align along y-axis, right? So initially suppose it is aligned along x-axis. So if I apply electric field, it will electric along y-axis, then it will try to tend along y direction. And if I define theta in this way, then it is a torque, you know, P cross E, already you know. Now I am finding the work done, okay, and relating it to the energy. What is the actual initial theta? It is obviously with pi by 2, you know, because y and x axis are mutually perpendicular, you know it, pi by 2. And work done, if the final position is theta, so it is obviously theta. And if I perform the integration, you will see like this, p cos theta. And if I write in the vector form, it is p dot e, right? So this is the energy. Now we will find interaction term. I mean, if there is two dipole moment. Uh, okay. So one is P1, another is P2. Suppose two dipole moment, and it is separated by a distance r. Then what will be the interaction energy? Already we have find out the electric field for a dipole, and first of all I want to find interaction energy at the P1 position. Hmm. So, electric field at P1 for P2. So there will be only electric field for P2. Uh, so it is. I'm writing this E2 as a E2. It is like this way. Already we have find out this. I mean equation. Just we have replaced P as a P2. And so energy at P1 will be, already we know, energy will be the dipole moment dot electric field. So simply this is P1 dot E2 minus P1 dot E2, and if we put all the things here, we'll find this expression. So similarly you can find I mean energy at P2 position, and you will see that both the term will be the same. So this is the interaction term, and this is also an important expression. Please remember, at least if, this electric field expression. If you remember, and also the energy term, you easily can find this interaction energy. Now we will uh, go inside into the main thing, that dielectric properties of matter. So, so uh, most everyday matter actually can be classified in two divisions. First one is conductor, and second one is insulator, or I can say it is dielectric. Okay. For conductor, you know that is a as there are lot of free charges which can roam around at their will, right? I mean, if you apply electric field, they can be rearranged easily, because all the charges are free. But for the dielectrics, it is considered that all the electrons, or you can say charges, are actually attached to some specific atoms. Attached. I mean, they are not free actually. They are, you can, in other way you can say, they are bounded to somewhere. Somewhere. So for that case, what will happen if we apply electric field? This is the actually main motivation on this uh, class actually, on this video. This is the main motivation, that what will happen if you apply electric field in dielectrics. So uh, there is also two classification of dielectrics. One is non-polar and another is polar. So from the naming, you easily can guess that what is non-polar. that there is no actually polarity. That means there is no permanent dipole moments in the material. Hmm. So for that case, I mean, I'm discussing in an atomic level. So I will consider the atom. If there is no permanent dipole moment, and I apply electric field, so there, uh, what will happen actually? The negative and positive charge clouds uh, will create a separation. So you know that for suppose if I talk about for water molecule, suppose. Hmm. So you know already no, water molecule is a permanent dipole moment. So for other, suppose which is actually non-polar, like I think is it carbon dioxide? Okay. So any other non-polar molecule, if you think about any other molecule or atom, so you know that actually negative charge is consist of electron cloud and positive charge is actually consist of nucleus. So there will be the same, I mean center of the positive charge and center of the negative charge will be separated by a distance if we have an electric field. So simply there is a creation of a electric dipole. Okay. Now this thing actually, this dipole moment is actually proportional to electric field. Hmm. And this proportional constant alpha is called actually atomic polarizability. And for the polar case, so already I have told that all this there is a permanent dipole moment in it. Hmm. so so the physics on this dipole moments will be same, already we have discussed in previous slides, that if, what will happen the dipole moment in the uniform electric field, what will be the non-uniform electric field. Okay, same thing happen actually here, will happen here. Actually that's why we have we have learned all those things for this purpose actually. Hmm. That for so for the polar cases, the thing will happen, already we had discussed in the previous slides. Hmm. So actually finally these two mechanism actually will keep the same basic result. What is that? That actually all the so we have considered that all the dipoles are very tiny. So all the these tiny dipoles will point along the direction of the electric field, right? So in other way you can say that the material got polarized. And uh, the measure actually there should be a measure of something. I mean this we are saying that the atom got polarized, that atom got polarized, so there should be some measurement, right? That this is more polarized, this is less polarized. So the measure is actually polarization. What is polarization? It is actually dipole moment per unit volume. So now for this polarization, from this polarization, now we see that, uh, that actually the effect of the polarization will give or will produce some charges inside the dielectric dielectric material, and we call those charges as bound charges. Here you can see this is a mm, potential for a single dipole. Okay, already we have uh, calculated this potential. Now, if we replace this dipole moment by polarization vector, you, you know what is this dipole moment. You can say small p equals to capital P dv dash for a volume element, and so total potential will be like this, integrating over the total volume, mm, and replacing p small p by capital P. So then this 1 by r, gradient of 1 by r, can be written as this harmonic vector by r square, Cayley r vector by Cayley r square, you know. Hmm? Now I am replacing this thing here, r inverted by r square by gradient Genoa, and just I will simplify uh, this is by this I mean identity gradient divergence of f is scalar and a is vector, then this can be written in this way. Just I have just rearranged the thing. And finally applying Stokes formula, you can see here it's a volume to surface integral, and this is same thing, volume to volume. And so you can see that this can be written as in this way. The one is surface charge density and another is volume charge density, right? So so this is actually surface charge density and this is volume charge density. Mm. so uh, so now you can see that that potential is can be expressed as a surface charge density and volume charge density. So from where actually these charges have come? Charges have come. This is actually due to polarization. So the and in Griffith, you can please look at the thing, that the physical significance of these bound charges. Please look at the things. This is very interesting. Because I have a time limitation, and also in video it is not possible to make you understand all those things. What is possible in the actual class, it is not possible in video, so I have not discussed those things. Please go through the Griffith. I think you will not face any problem. So this is a surface charge density and this is volume charge density, right? So now we'll apply Gauss's law in the presence of dielectrics. So naturally, uh, the total charge uh, will be, you know, that one is for the polarization, and this is the volume charge. I'm talking about the volume charge density. One will be for the polarization, that is bound charge density, volume charge density, and another will be for the everything else. I mean, I'm calling it free charge density, free charge volume density. So if I apply Gauss's law, this is simply, you know, I'm applying. So epsilon 0 divergence equals to rho. It can be written rho b plus rho f, and if I place the actual term of rho b, that's bound volume charge density, by minus divergence p. This is a polarization vector, you know. And if I rearrange the thing, you will find you can write the expression in this way. Here D is an electric displacement vector. Electric displacement vector. So in integral form, it can be written as this. Uh, now this is the actually Gauss's law in dielectrics. And now uh, we'll do a more simplification. Uh, Precisely, I can say that we are trying to find out what is the actually permittivity. Actually, what is permittivity and what is actually dielectric constant. We're going to find out all those things. So that's why we need uh, more little bit more uh, information, that is linear dialectics. So what is linear dialectics? Actually, many substances polarization depends on the electric field. I mean, in all, actually in all substances polarization depends on electric field, but in some substances it it is linear proportional to electric field. So you can see here chi and named it chi is a proportional constant. And we call it electric susceptibility, and this epsilon 0 actually extracted here to make chi dimensionless. So you already know that what is linear dielectric. So if someone asks you that what is linear dielectric, you can say that if the material of a this p equals to epsilon 0 chi e vector, electric vector, then is called linear dielectrics. So in linear dielectric media, so in dielectric media actually you can write D equals to epsilon 0 E plus P, and if you replace P by linear dielectric formula, then you can find this type of expression, right? Epsilon 0 1 plus chi E into E. So you can write in a simple way. This is you can replace this epsilon 0 1 plus chi E as epsilon. This epsilon, we call it permittivity of the material, and epsilon 0 is the permittivity of free space, right? Again, this epsilon by epsilon 0 is called the relative permittivity. What is actually dielectric constant of the material? This is all the actually information and the simplification. So you have to remember all those things in exam, and also in future you may have need all these terms. Now we'll find the boundary conditions. So to find boundary condition, we need some equations, I mean very fundamental equations. One is divergence and another is curl. So for divergence D, it is can be written as rho f, and in integral form it can be written in this way. And curl, if I find curl of D, just I have replaced this epsilon 0 E plus P here. Just perform curl, since curl equals to 0, you will find curl P, curl D equals to curl P. Similarly, divergence E and curl E, and from these equations, from one you can find this. I mean, if I this boundary condition is that there is a boundary between two dielectric media, two media. So if I draw a line between the boundary, then this is the above and below. So you can find d perpendicular above and d perpendicular below is not continuous actually. So this is by discontinued by surface free charge density. Mm, and also for d parallel above and d parallel below, you can find this discontinuity. Only you can see here, only the parallel component of electric field is continuous, only so in doing problem you may have need this boundary conditions. So if you do problems, you will find these boundary conditions very useful. So today actually this was our plan to learn actually. So I don't know how much I have been able to teach you. I mean, make you understand all those things. Please comment on WhatsApp if you face any problem, and also please don't waste your time in this I mean in this time, because you have got maybe extra time for your course. And please read at your home, uh, and please stay at your home, be safe. Thank you.